In this module, haloalkanes and haloarenes, we will be learning about the nomenclature, preparation and properties of haloalkanes and haloarenes, and also how to do quick organic revision. Now, if we take haloalkanes, earlier the old name was alkyl halide. Alkyl halides are nothing but an alkyl group. We can write it as R, and halogen group we give it as X. So Rx is the common general name for an haloalkane or alkyl halide. R is the alkyl group. How do we get an alkyl group? From 3Cl. So this is from methane I get methyl chloride. This is the common name, or we write it as chloromethane. And if we write CH3, CH3, and we have a Br at the second carbon, we will write this as 2-bromo. What is the longest carbon chain? It is 1, 2, 3, so propane. So if I have an alkyl group and halogen, least number should come on the halogen. In general, if I have a haloarene, we have benzene and a halogen attached to benzene. These are haloarenes. So, or aryl halides. So, or we write it as C6H5X. If we have to write chlorobenzene, it is C6H5Cl. This is chlorobenzene. Now if we write it as C6H5CH2Cl, then this is C6H5CH2 is called as benzyl group. This is called as benzyl chloride. Now if we have the halogen is attached to a carbon which has 2 hydrogens attached to it. The chain is extending only on one side. These are called as primary halo compounds. If the chain is extending on 2 sides, I have R2CHX, then these are called as secondary, and R3CX, these are called as tertiary or 3-degree haloalkanes. If we have halogen attached to the carbon which is attached to a double bond, these are allylic. If the halogen is directly attached to the double bond, these are vinylic. If we have 3 halogens attached, then these are tri-halo compounds, and this will be 1, 2, 3 trichloropropane. And if we have 2 halogens attached, then these are dihalo compounds. The name would be 1,2-dibromoethane. Now this is a chart that is prepared where we are having the preparation and the properties given in the same chart. So this is what you have to remember at the end of the chapter. So you will have to remember 2 charts, one for haloalkanes, another for haloarenes. So one we have given preparation, the other is properties. Almost all preparation and properties are written here. In case you have to learn something else, you can add to the chart. So the first preparation is from, now you have to only do these in detail once, and after that you have to write it on a A4 sheet paper, this chart, preparation and properties. And at the end of your organic you will have about 7 charts, and if you reaction with names, almost most of the reactions with names are there in the chart itself, and a few distinction between can be learnt in a separate, you can write down separately and learn at the end, and some mechanisms. So let's see how we can learn organic quickly. So mostly what happens is the child forgets. If I say I want to prepare an alkyl halide, you tend to even forget from what. If I remember from, I will get the reaction. So what are the methods of preparation of chloroethane? We have taken, in general we have taken chloroethane. What are the methods? One, from alkanes. You have seen it in class 11th. That means if I take an alkane, halogen plus sunlight, I will get haloalkane. Or from alkenes, if I am taking an alkene, treating it with HCl, so the double bond breaks, I will get chloroethane and HCl is attached. Now in this you can see I have put this one. That means here if I am having an asymmetrical alkene, I have to remember Markovnikov's rule and anti-Markovnikov's rule. So Markovnikov's rule and anti-Markovnikov's rule. So from alkanes, this is in detail, the complete reaction is given, and then from alkenes I have Markovnikov's rule. So if I am taking an asymmetrical alkene and I treat it with HX, so the hydrogen will go to the carbon which has more number of hydrogens attached to it, and the X will go to the carbon which has the other carbon. So the double bond will break up, hydrogen goes to the carbon having more number of hydrogen, so this becomes CH3. Then you get X is attached here to the second carbon, and then CH3. Now in anti-Markovnikov's rule, this HX can be either HCl, HBr or HI. And anti-Markovnikov's rule you have done in class 11th. If we attach HBr in presence of peroxide, you have to remember both these, it is only for HBr, then the hydrogen will go to the carbon which has less number of hydrogens. This is the these are the two doubly bonded carbons. So this has 2 hydrogens, this has 1 hydrogen. So hydrogen will go to the carbon having less number of hydrogens. So Br will get attached to the other carbon. So I will get a 1 bromo product. Here I am getting 2. So mostly these reactions we are using when I have to change the position from 1 to 2 in a halogen compound. So next, what are we having? We have in the chart, so this is from alcohols. So from alcohols, if I take an alcohol, I may treat it with HCl, ZnCl2 or SOCl2 or PCl5 or PCl3. So any of these reagents, I will get an alkyl halide. So we apart from if the reaction is asked separately to complete the reaction, we are using these reactions only. I have to remember any one. Either I want to convert an alcohol to alkyl halide, I may just use SOCl2, RCl, SO2, HCl they are gaseous products, I'll get an alkyl halide. Or just remember HCl, ZnCl2. Now all these reactions are important. You should know for these reactions that I have given in red, you should know the byproducts also, because these reactions are coming for complete the reaction. So PX3, I will get RX plus H3PO3. For PCl5, I will get POCl3 and HCl. And NABR H2SO4, I will get NaHSO4 and water. These are the byproducts that are present. So this is the third method, and by halogen exchange also we can prepare haloalkanes. So if I take RX, where X can be chlorine or bromine, and treat with sodium iodide, I get a iodo product. And to get a fluoro, if I take CH3Br, treat it with AgF, I'll get fluoromethane. So all the methods, all this that you are writing down every time in detail, everything we have put it in one small preparation of haloalkanes. Here all the methods are given. So it just takes you 2 minutes to revise or 5 minutes to revise the whole complete chart of preparation and properties of haloalkanes. Now if we come to the properties of haloalkanes, should know a few physical properties. And then now haloalkanes are colorless when pure, lower members are gases and higher members are liquids. The boiling point increases with increase in number of carbon. This is a common physical property for all hydrocarbons. If we have less number of carbons, the boiling point is less, and as the carbon chain increases, the boiling point is going to increase. So if I'm saying bromomethane and bromoethane, and if I have to compare their boiling points, then boiling point increases with increase. The boiling point of bromoethane, the molecular mass is more, so it will be more than that of bromomethane. Similarly, boiling point decreases with increase in branching. Now if the branching is more, the branching is more, this is tertiary butyl chloride and this is secondary butyl chloride, the branching is more here, then the boiling point of tertiary butyl chloride will be less than that of secondary butyl chloride. As the branching is more, the surface area will become less and there will be less van der Waals force of attraction, and the melting point of para isomer is higher as compared to, so if I'm having dihaloarenes, then the melting point of the para isomer is more. Now if we see the chemical properties, then all haloalkanes show nucleophilic substitution reactions. So what are nucleophilic substitution reactions? Nucleophile, if I say nucleophile, it is nucleus loving. So nucleus is positively charged, so nucleophile will be negative, either negatively charged or has a pair of electrons. So nucleophile is attacking the halide R. So if I'm say NaOH, so what is the nucleophile in NaOH? NaOH, the OH minus is the nucleophile. NaOR, the OR minus is the nucleophile. So this bond Rx is, the halogen gets a slight negative charge and the carbon gets a slight positive charge. So the electronegativity of the halogen is more, so X is removed, halogen is removed as X minus, and the nucleophile gets attached to R. So I'll get R plus the nucleophile. Now this nucleophile can be OH, Then aqueous NaOH, I get an alcohol, and if we have OR, NaOR, I'll get ethers. If it is KCN, you have to remember these products. KCN will give you nitriles, RCN, CH3CH2CN, and with AgCN you will get isonitriles, NC. With KNO2 I get nitrites. With AgNO2 I get nitro compounds. With ammonia and heat I get amines. And if I treat with lithium aluminum hydride, I am getting alkanes. So all these reactions we have put in the chart that we have prepared. Similarly, elimination reaction, this reaction is also important. With alcoholic KOH, the H and one halogen and one hydrogen are removed to give an alkene. So whenever if I want to prepare an alkene from an alkyl halide, I will be using alcoholic KOH. Other reactions, if I take RX and sodium, I'll get RR. This is Wirtz reaction we have done in class 11th. RX plus magnesium, I get Grignard's reagent, RMGX. With CH3CH2Cl, if I take benzene AlCl3, I will get the alkyl group will be attached to benzene. This is Friedel-Crafts reaction. And if I want to get back alkane from alkyl halide, I treat with hydrogen and nickel. So these are the reactions of alkyl halide that we have to remember, and all these reactions that we have to remember are put again in this chart. So this is the preparation, this is the properties, all the preparation and properties are given in the chart. The nucleophilic substitution reaction, elimination. So we can learn the preparation and in mechanisms of haloalkanes. We have two mechanisms. One is called as the substitution nucleophilic bimolecular or SN2 mechanism, and the other is SN1 mechanism. So if we take a nucleophile, so what is the nucleophile here? OH minus in general, this is the nucleophile. So if we take a nucleophile, treat it with haloalkanes, I'll get alkyl group and the nucleophile, and chloride is removed. Now what happens is in SN2 mechanism, I have a carbon which is attached to 3 hydrogens, and the chlorine is attached, CH3Cl. So as the nucleophile approaches the haloalkane, the chlorine starts moving away from the carbon. So chlorine moves away from the carbon, and the nucleophile OH minus starts coming close to this carbon. So this OH minus is slowly coming closer to the carbon of the alkyl halide, and the chlorine is moving. So this is the intermediate product that is formed, and later the Cl is removed as Cl minus, and you get alcohol. So in SN2 mechanism, in this step, if we see this, in this step where we are having the unstable intermediate, in this step we have this is a slow step, and 2 reactants are involved. The nucleophile and the alkyl halide are involved in the slow step. Therefore it is a second order reaction, and it is called as SN2 mechanism. Now if the groups attached close to the carbon, if they become heavier like methyl tertiary or secondary, then it is difficult for the halogen to get attached to the carbon. So if I'm having, instead of this, if we say we have a secondary or a tertiary carbon. So what is a tertiary carbon? I have got 3 methyl groups attached to this carbon. So we have 3 methyl groups, so and a halogen. So halogen is moving away, but as the nucleophile is approaching here, there are bulkier groups present. So it is more difficult for the product to be formed. So the reactivity in this case would be primary halide is the most reactive, secondary halide is less after that, and then the tertiary halide. This is important. You get problems based on this SN2 mechanism. So what I should know, that it is second order, and there is inversion of configuration. The OH is attached on the opposite side to what the halogen was attached. In SN1 mechanism, mostly tertiary halides undergo SN1 mechanism. In SN1 mechanism, the first step involves, which is a slow step, it involves heterolytic fission of alkyl halide forming a carbocation, C plus, positive charges on the carbon. So this is a carbocation that is formed. This step is slow, involves only one reactant, therefore it is first order reaction, and this carbocation quickly reacts with the nucleophile, forming the product. The reactivity in this SN1 mechanism is benzyl, then allyl, then tertiary halide, secondary halide, and primary halide. It is just the reverse of SN2 mechanism. And reactivity both for SN1 and SN2 mechanism, iodides are more reactive than alkyl bromides, then chloride, and then fluoride. So you have to remember both these reactivities. Mostly whatever you have to remember, I have put it in red. So these are the two mechanisms that you should know, SN2 and SN1. And there is one problem that generally these are the problems that are there in the examinations. So arrange in increasing order of reactivity towards SN1, SN2, 2 bromomethylbutane, 1 bromopentane, and 2 bromopentane. So I have written the structures of these three products that are given. So you have to just check up which is primary, which is secondary, and which is tertiary. So this B, this is the carbon chain is on 3 sides. There is no hydrogen attached. So this is a third degree or tertiary alkyl halide. This is 1 bromo, this is secondary, this is primary 1 degree, and C is 2 degree. So if we take, you can remember SN2, the lighter groups are more reactive in SN2 mechanism. That means primary more reactive. So in SN2, so we have to give increasing order. So the most reactive would be B. B is most reactive. Then you have secondary, then C, and then A. And the order is reversed. For SN1, it will be B, then C, then A, which will undergo SN2 reaction faster, CH3 2Br or CH3I. So as given earlier, the iodide are more reactive, so it will undergo reaction faster. So this is for haloalkanes. And then one more reaction mechanism you should know. This is called as Sedzeff rule for beta elimination. So if we have an during hydrohalogenation, that means if I treat it with alcoholic KOH, alkyl halide, the hydrogen is removed with Br, forming a double bond, alkene. So from which side, if I am having an asymmetrical alkyl halide, the hydrogen is removed from beta carbon, which has greater number of alkyl groups attached to it. Now this is the alpha carbon, the bromine is attached here. We have beta carbon this side and this side. So if I am taking this beta carbon, there are two alkyl groups attached to this. If I am taking at this position, there is one alkyl group attached. So it will be removed from where there are more number. That means this Br plus one hydrogen from the third carbon is removed, and you get this. The major product is you are having 2-pentene. Now let us see the chart for preparation and properties of haloarenes. Like haloalkanes, we have put it in one single chart. This is the preparation and then the properties of haloarenes. So we have two methods of preparation of haloarenes. One is from benzene, the other is from benzene disonium chloride. So we have two methods. One is from benzene. So directly you would have done last year benzene. If I treat with chlorine in presence of a Lewis acid like AlCl3 or FeCl3, I will get chlorobenzene. Similarly, if I take toluene C6H5CH3, treat it with halogen in presence of Fe or halogen in presence of AlCl3 or FeCl3, I will get. So this CH3 group is ortho-para directing. So the incoming halogen will go to the ortho position or go to the para position. Alright, and the second one is benzene disonium chloride, preparation with from benzene disonium chloride. This reaction is also called as Sandmeyer's reaction. So this C6H5N2Cl, this is called as benzene disonium chloride. If I treat it with Cu2Cl2HCl, I get chlorobenzene. Cu2Br2HBr, I get bromobenzene. And for iodine, I treat it with Ki, I get iodobenzene. And how do we prepare this benzene disonium chloride? If I take aniline, treat it with NaNO2HCl at 0 degree C, I will get benzene disonium chloride. This Sandmeyer's reaction is important. Now if we see the properties, they undergo nucleophilic substitution reaction. Now this arene is not as reactive as if I am taking chlorobenzene. It is more difficult to remove this Cl as Cl minus in case of chlorobenzene than in case of Rx. So reactivity of chlorobenzene is less as compared to haloalkanes. So it is more difficult to remove the halogen in case of haloarenes than in case of haloalkanes. So when we are taking the properties, if we say nucleophilic substitution reactions, then these nucleophilic substitution reactions, they in case of Rx, we would have just treated with aqueous NaOH. Here to remove the halogen, we have to have certain conditions. You have to remember the condition: 623 Kelvin, 300 atmosphere pressure. Second, I treat it with an acid H+, I get C6H5OH phenol. Similarly, if I have to get an amine, I treat with ammonia, Cu2O, 475 Kelvin, I'll get ammonia, and this is called as Dow's process. Reaction with metals, if I take ARX or C6H5Cl and treat with sodium in presence of ether and an alkyl halide, the R gets attached, this R gets attached to the Cl is removed and R is attached. This is Wirth-Fittig reaction we have seen last year. And if I, instead of R, if you have another C6H5X, then the C6H5 will be attached. Here chlorine, chlorobenzene, I treat with sodium and ether, I get diphenyl. This is Fittig reaction. So we have Wirth-Fittig and Fittig reaction. Both of them are aromatic rings, then it is called as Fittig reaction. If I take chlorobenzene, treat it with nickel aluminum alloy, NaOH, I get back benzene. So for benzene, chlorobenzene, you have a benzene ring, so you have an all compounds with a benzene ring. We can have ring substitution, that means halogenation, nitration and sulfonation. This is common whether I am taking chlorobenzene or phenol, or I have aldehyde group attached to benzene ring. So these chlorobenzene is ortho and para directing. That means the incoming group goes to the ortho position or para position. We will be seeing soon why it is ortho and para directing. So you should remember chlorobenzene or aryl halides are ortho para directing. So this incoming Cl group will be attached to the ortho position or the para. So you will get 1,2-dichlorobenzene or 1,4-dichlorobenzene. Similarly, nitrating agents are HNO3 concentrated H2SO4, I get nitro product. Sulfonation, I'll get SO3H is attached. So either at the ortho or para position. And which is the major product? The para product is the major product. Similarly, you have seen this reaction in class 11th. Chlorobenzene, if I treat it with an alkyl halide and anhydrous AlCl3, this is alkylation of chlorobenzene. Alkylation and acylation of chlorobenzene is called as Friedel-Crafts reaction. So alkylation, alkyl halide, the alkyl group gets attached to the reactant at the ortho, and because it is ortho para directing, at the ortho and paras. In acylation, CH3COCl, so this acyl group COCH3 gets attached either at the ortho or at the para position. So all these reactants that you are having, preparation and properties of haloarenes, we have put in one chart that we have seen earlier. So preparation and properties. So you have to remember only two charts, for one chart for haloalkanes, one chart for haloarenes. Now we should know why haloarenes have low reactivity. So in most of the halogen derivatives, you should know how to write the resonating structures. So if I am taking the haloarene, chlorobenzene, then these are the double bonds. We have a chlorine group attached, and how many electrons are present on the chlorine group? Chlorine has 7 electrons and 1 electron is used up in the bond, and 6 electrons are 3 pairs of electrons are present on the chlorine. Now this one pair of electron can form a double bond between chlorine and this carbon, and this double bond will shift to the ortho position. So you should just learn how to do this shifting. At any one time there will be two shifting. So what will you get? The next resonating structure that you get, we have shifted here, so this becomes a double bond Cl, and how many pairs are left now? We have only two pairs or 4 electrons left on the chlorine. So chlorine gets a positive charge because it has used up its electron, and this double bond comes at the ortho position, so it gets a negative charge. The other two bonds here and here, they remain the same, so you have these two remain the same. Next shifting, I will show one more shifting. There is a negative charge, so this negative charge can form a double bond between these two carbons, and this bond will shift to the para position. So what will you get? Once you learn the other, there is no change in the rest of the atoms. So this is still with a negative charge. You get a double bond here. This comes to the para position, and this bond remains the same. So chlorobenzene shows resonance. Now due to resonance, you can see that there is a positive charge developed at the chlorine, so it is more difficult to remove the chlorine as Cl minus. And similarly, there is a double bond which is being formed due to resonating structures. Here double bond is formed, so it becomes more strong, so it is more difficult to remove the Cl as Cl minus or for nucleophilic substitution. So if you have to explain why it is more difficult, it is because of the resonating structure. You should learn how to write the resonating structures, and then also you can see the negative charge is coming at the ortho and para position. That means if there is a negative charge on the ortho and para position, the incoming ring substitution or electrophilic substitution will take place at the ortho and para position, and that is why chlorobenzene is ortho para directing. So I have given here, so less reactive towards nucleophilic substitution because of resonance, and also because the carbon here is sp2 hybridized and the S character is more. Here I have given the two charts that you have to remember, both for haloalkanes and then also for haloarenes. So these are the two charts that you have to remember. Without the markings, I have put it again. And then how do we distinguish between haloalkanes and haloarenes? Now if we treat the two with aqueous KOH and neutralize with dilute nitric acid and treat with AgNO3, a white precipitate or a precipitate light yellow in case of a bromide and yellow in case of an iodide, you will get a precipitate, and for alkyl halides, and no precipitate for aryl halides. So what happens? Suppose I am taking Rx, this is Rx, and aqueous KOH, what do we get? I'll get ROH and KX. This KX, suppose I am taking this as Cl, you will get KCl. So KCl reacts with AgNO3 forming AgCl precipitate, which is a white precipitate, and KNO3. So you will get a precipitate in case of an alkyl halide and no precipitate in case of an aryl halide. So if I have to distinguish between chlorobenzene and chloroethane, this is alkyl halide, so this will get a precipitate and no precipitate in case of. So similarly, chlorobenzene and chlorocyclohexane, this is an aryl halide, no precipitate. What is chlorocyclohexane? This is cyclohexane, and chlorine groups are attached to. This is an alkyl halide, so this will show a precipitate with KOH and AgNO3. So you should be able to distinguish between the two, and let's try a few conversions. Let's start the conversions, and then as we proceed along with other organic chemistry charts, we will learn further conversions. So in this chapter we should know, we have done Markovnikov's rule and anti-Markovnikov's rule. So mostly this is used for changing the position. I want to convert 1 bromopropane to 2 bromopropane. So what do we do if I have to get 1 bromopropane to 2 bromo? Markovnikov's rule, anti-Markovnikov's rule, I'll get, if I have an alkene, that means this reactant that I am having, what is this? 1 bromopropane, we should be able to first convert into an alkene. So how do I convert an alkyl halide into an alkene? You should remember in the chart, just see the chart. Suppose I see the chart of haloalkanes. How do I get an alkene from an alkyl halide? How do I get an alkene? Alcoholic KOH. So first I should treat it with alcoholic KOH. Alcoholic KOH. I'll get an alkene. So this Br, hydrogen from the next carbon is removed. I will get an alkene CH3, CH, double bond, CH2. Alright. So this alkene, once I get an alkene, I want the halogen at the 2 position. So if I want the halogen at the 2 position, the hydrogen has to go to the 1 position. That means carbon containing more hydrogens. It is Markovnikov's rule. So if what should I treat it with? I'll treat it with HBr. So if I treat it with HBr, what do I get? The hydrogen will go to the carbon containing more number of hydrogen atoms. So I will get CH3, CH, Br will come to the second position, and CH3. And if I have to reverse this 2 bromopropane to 1 bromopropane, then I'll first convert it into an alkene, and then I want it at 1 position. So I'll treat it with HBr and peroxide. I will get the bromine at the 1 position. Now if I have to convert benzene to diphenyl, so benzene, what I know, if I can get chlorobenzene, I'll get diphenyl. So how do I get chlorobenzene? Treat it with chlorine in presence of AlCl3, Lewis acid. I will get chlorobenzene, and once I get chlorobenzene, what should I do? If I treat it with sodium in presence of ether, Wirtz reaction, I will get diphenyl. So there are simple conversions given in the textbook. Try the conversions. Just keep the 2 charts in front of you. Try to do the conversions by looking at the charts. You would be able to do the conversions. So you have to remember the 2 charts, and also remember a few mechanisms: SN2, SN1, Setsev rule, and then the reactivity of haloarenes. So that is all for haloalkanes and haloarenes. Please practice, write and practice these questions. Once you have written down, after that you can only go through the charts. You have to go through the charts daily or after alternate day. It will take you just, for these 2 charts, just 5 minutes. You will be able to remember organic chemistry. Thank you. Please like and subscribe to my channel, Learn with Neera Sharma.